the exercise are playing around the MMC estimation now, okay? The orthogonality principle, actually, we already touched it, but you know, that means that we know where it comes from, okay? And we have a Wiener filter that we can work with. Now let's start with the first one. So I choose this, but you know, I mean, half an hour ago I was surfing through the exams to pick up 1, 2, 3. I found 3. Now, so let's read it together. What do these say? Now, here I give you the block diagram. Okay. Now, in other case, I don't give you the block diagram, but you know, I strongly encourage to write a block diagram, because from the block diagram you can see, for instance, that you know, I mean, if this is the input, this is the output, the two outputs are coming from the same input. Now, by the equation, the equation are saying the same, but you know, if you see it, it's better than, you know, I mean, creating or figuring out or mentally think on that, okay? No. So, we have a random process, alpha, which is a Gaussian with a unitary power, okay? And this is alpha. And then we have a W, and W is another Gaussian random process with the sigma square as a power, as a variant. Now these are two statistically independent wide random processes, and I get two corresponding signals generated by filtering. More specifically, X is equal to a certain way and Y is equal to another way. Now, so that means that putting in a graph, okay, putting in a graphical way, that means that X is coming from alpha by a filtering, and this filter is 1 plus z to the minus 1. This comes because I take these relationship, this finite difference equation, I Fourier transform, and I can see that it's 1 plus z to the minus 1, okay? Plus W is a noise. So X is noise plus this filter. And Y is taking the input and filtering by 1 minus z to the minus 1. So I have 1 plus, 1 minus. Now, you know, you probably, when you read something like that, I suggest you to start elaborating a little bit. So first of all, this is a 0, this is a 0. So I have a 0 in a position, a 0 in another position. So I have a 1, 0 in 1 and 1, 0 in minus 1. In other words, so the sketch of this is that I have 2 zeros, but you know, in the first case, 1, 0 is here, and this is for the filter. Let me say, how do I call it? H is used, we say F1 and F2. Okay. So this is the 0 in F1, and then I have another 0 in due to the F2. Okay. So now, what I'm asking, because I want that you understand, I'm asking you, characterize the two processes X and Y. Okay, they are moving average. Evaluate their autocorrelation sequences. Okay, very simple. Evaluate the power spectral density for each of the sketch the two power spectral density versus angular frequency for sigma W equal 1 divided by 110. So, you know, the power spectral density as the output of each of one is the following. So, let me write here because we have a space. So, the power spectral density Sx omega, okay, is the power spectral density of the noise, which is sigma squared, plus the power spectral density of the input, which is sigma squared alpha, which is the power input, okay, multiplied by F1 omega squared. Okay, this is the power spectral density. Now, you know, if rather looking at this way, okay, So the power spectral density is the autocorrelation sequence on X, okay, calculated for Z equal AJ omega. And you know, and the autocorrelation Rx Z is equal to sigma squared W plus sigma squared alpha times F1 Z F1 star 1 over Z. Okay, that's it. So you know, since I have two zeros located here, so since I have 1 0 located here, in the power spectral density I have two zeros. Okay? So this is what I expect. So you know, now the power spectral density essentially, it is the power spectral density of this guy here, where sigma alpha is equal to 1 and sigma W is 1/10. Okay? So let me keep a parametric with respect to that. So that means that the power spectral density of this part, let me write it this way, of this part, okay? So the power spectral density of this part is limited between minus pi and pi, 0. For F1, I have a 0 here. Okay? So essentially what I expect in the power spectral density for this one is something which is behaving approximately this way. How much is the gain here? How much is the power spectral density at the maximum? You know how to compute? So the power spectral density at the maximum. This is the power spectral density, let me say. This, what I sketched, let me write a little bit lower so that I can write on the top. Okay, this is the power spectral density of this part. Okay. So what is the value? So what I know about this power spectral density is that it goes at a 0 here. Because there is a 0. There are two zeros. It goes in the power spectral density, we have two zeros coincident. Okay, now, you know, what is the value in omega equals 0? What is the value in omega equals 0?
0.
Huh?
Rx in 1.
Rx is sigma omega.
Rx is equal 1, right? But you know, how much is that? I want to know how much.
4 sigma plus 1.
What?
4.
4. Okay. Perfect. So in 0, the power spectral density is 4 times sigma squared alpha, which is 4. Okay? So we can sketch it. The reason, do you know, someone doesn't know the reason? The reason is that I'm computing the power spectral density here. I have a 0 there, so this distance is 2 to the square makes 4. Okay? So, you know, since to this power spectral density, I need to sum, to put on the top the power spectral density sigma W. So the total power spectral density, let me sketch it. So the total power spectral density is a constant value and then the other on the top. Okay, where this constant value is sigma squared W, which is 1/10. Okay? So the power spectral density here is, the value is 1/10, and here is 1/10 plus 4. Okay? Sketch it. So right. Now, what is the power spectral density for Y? Okay, what is the power spectral density for Y? You know, looking at Y, the filter is the same, except that, you know, where I have the frequency pi, I have 0, where I have 0, I have pi. Okay, according to the value. So now I can easily derive the power spectral density for y. So from this one, I can easily get, so this is the order of solving. I solved this one first, then I solve this one to follow. And so I don't need to generate anything because I can easily derive the power spectral density for the second, for Sy, and then it is, it's behaving this way. Okay. This is for F2. So Sy omega, power spectral density, is the same except shifted. Okay, shifted by pi, because I have the same configuration of zeros. So the maximum value is 4, and here I have 2 zeros. Okay, so answer number 1, you know, it's straightforward. Now let's move a little bit deeper. Now estimate the y, okay, by the MMSE criteria. So my goal is to estimate the value here by the MMSE criteria using x. So that means I know x, I want to get y. Now before that, there was a question. Yeah, let me answer to the question C. If there is no noise, there is a simple intuitive way to estimate y that requires almost no computation. Can you show how? So the goal is estimate y from x. Okay, that's the question. So, you know, if I want to estimate y from x, what I need to do is to invert this filter and multiply by that. Okay, because I mean, if I want to estimate y from x, I need first to estimate alpha from x. So how do I estimate alpha from x? I need simply to apply a filter with one pole, okay, so that the pole cancels with a 0. Then, you know, what about getting y? Well, if alpha is estimated in this way, then you know y is simply obtained by applying the second filter. So I prefer to answer to this stupid question because I mean it's giving me the optimal solution in case of no noise. Okay. Now if there is noise, this is not the optimal solution. Because I mean what I'm doing is I am applying, so I'm using a filter with one pole. So if I have a pole here, which is the inverse of this filter, the pole is amplifying the noise. So I have a filter with one pole which is amplifying the noise, and then you know I have another 0 which is not zeroing the noise in the power spectral density as it should be. So I get an amplification of, which is uncontrolled, of the noise. And this is something that I don't want. So making, you know, taking, let me take this one and I transport all over the
It's like a bakery.
is not copied. Now it's copied. Okay, so the page. Okay, so let's answer the former part. So if sigma w is equal to 0, that means no noise. The trivial way to solve it is that alpha estimated n is obtained in the Fourier transform or Z transform by taking xz, okay, and then multiply by a filter which is 1 over 1 plus z to the minus 1. Okay, that's a filter. Now, since in this case, this is the optimal estimate, now if I want a y hat then, is by taking the, the estimated alpha and then multiplying. So it is ixz is equal to multiply by 1 minus z to the minus 1 and 1 plus z to the minus 1. This is the optimum. Okay, I don't need to touch any equation. Okay, so it's the obvious one. Which means I need to calculate from here going there. Now, what about, what's happened with the noise in this case? Why is not optimal? It's not optimal because, if I also include the noise, then, let me say, a hat z, which is the noise, is equal to xz divided by 1 plus z to the minus 1, which is fine, plus wz divided by 1 plus z to the minus 1. Okay. So that means that the noise is amplified by a filter that has a pole here. Is it clear? Okay. So that means that the corresponding power spectral density is approximately shaped in this way. It has, big value and then a big value, which is going to infinity if you want. Okay? So there is an uncontrolled amplification of noise, which means it's not a good estimator for alpha hat. Okay? The most intuitive. Now let's touch the equation. Is it clear? Okay. Now we tell me.
There is no noise in the question, so why?
No, I am showing you that what's happening in case I apply this solution to the case at the moment. Okay, and and it comes out that it's not optimal. So what I get is I'm not expecting this as a solution. Okay. So now now let's read. Okay, the question which is asking. Now I postpone the solution of B after. Use the Wiener filter theory to estimate Y from all the samples, for all the samples of Xn for any arbitrary sigma W, which is any arbitrary power of node. Compute the linear estimator of Y hat equal H convolved X and evaluate Hz for the limiting case when sigma W, sigma square going to 0 and sigma square going to infinity, which means small and a large enough power of noise. Okay. Now, so let's go to the point. Now, this is asking about the Wiener filtering. Okay. So that means that my estimator is obtained by Wiener filtering. Now, let's derive it. Okay. Now the Wiener filter says that my goal is to estimate y hat. So in Fourier domain, I want to estimate y at z as a filter h z multiplied by x z. Okay. So I know x and I want to get y. So what is the error? The error epsilon z is equal to y z minus y hat, which is h z times x z. So by the Wiener filter theory, you know, the estimator is the following, is by the orthogonality principle is the expected value of the error time the signal which is used to estimate the filter, which is x star 1 over z. This is equal to 0 by the orthogonality principle. So for MMSE, Wiener, I use the orthogonality condition. In Z transform. Okay. Now, so let's see what is the error. So we copy it. So I have the expected value of. Let me arrange. So I have H there. So it's the expected value of x z, x star 1 over z multiplied by h z is equal to expected value of y z multiplied by x star 1 over z. So for the filter, I need to calculate the z transform, so which is Rx x z, and I need to calculate Ry x z. Okay, that's all I need to compute. Now, what is Rx x z? You know, actually we computed already. So now this one is it's a unitary, so it is sigma squared plus this unit, so it is 1 plus z to the minus 1 times 1 plus z. See page C before. Now, how to get the other? Now, so we need to compute the correlation between here. We need to compute the correlation between y and x. Okay. Now, so what is y? Y is alpha filtered by f1. Okay. So, you know, if I want to compute this correlation, then y is alpha multiplied by f1 plus the noise. Now, you know, let's compute that. So it is expectation of, now y, okay, y is alpha, which is the z transform az times f1 z plus wz multiplied everything times x star.
Why plus W?
It's a noise.
But that's X. X
Oh, I
is
swapped the signals. Thanks. I swapped the signals. So x, so y, you know, what I can do is this. Y, z, and then x is equal to a star 1 over z times f1 star 1 over z plus w star. Now this and this two are equal 0 because they are mutually orthogonal. Okay, they are uncorrelated. It's noise and the input. So, you know, this becomes, for this reason, I need to new page. I take everything and put a new page now. simply copy it. Still our problem in front and the other part. Here it is. Okay. So since that one is equal 0, then I continue. It's what I need to compute is the expectation of y z. Now a is a stochastic. And then I have f1 star 1 over z. Now what is y? Y here is az times f2 z. Okay? So putting everything, grouping together, okay? So it comes out that this is equal to expectation of, so it is f az a star 1 over z, then it is out of the expectation because f1, f2 are deterministic, so it is f1 star 1 over z, f2 z. Then I group all together, okay? So the estimator I call h, I guess. H, yes. So hz, which is the winner, okay, is equal to, so it is f1 1 over z f2z multiply by sigma square alpha, which is unitary, if you like, which is equal to 1, and then the denominator was the power on x, I guess. Yes. So it is sigma square plus this f1z f1 star 1 over z. Okay. Now multiply by sigma square alpha, which is unitary. So it's 1. Okay, this is the Wiener filter. Now the problem asks us, okay, if you like, I can also write in the following way. So it's sigma square plus 1 plus z minus 1, 1 plus z. And the numerator is f2, which is 1 minus z minus 1. And f1 star is 1 plus z. Okay. That's the Wiener filter. Now the Wiener filter, has 1 0, 1 pole, and it contains 2 zeros. Okay. The one pole, sorry, it's 1 pole, it's 2 poles. Made a mistake. Okay, but the 2 poles are, they might be inside and outside of the circle, and this gives rise to the impulse response, which has an infinite support. Now, let's answer to the question. The question says, what's the filter? For sigma square going to 0 or going to infinity. Okay. Now, what is the, I don't know, we can study here or there, doesn't matter. So the easy is if sigma square is going to infinity, which means, we have a lot of noise. Now, if I have a lot of noise and my goal is to estimate the output here from the input, when the noise is going to infinite, so what I'm going to do is that it's better to use the a priori. Let me repeat, okay? So, if I need to calculate the power here, we estimate this guy, and the noise is very big. So what's happened is that, you know, if the noise is so big, then there is no signal, almost no signal. So that means that X and Y are uncorrelated because it's dominated by the noise, okay? So now, since they are almost uncorrelated because X is noise only, it's dominated by noise, now these two guys are uncorrelated, right? So what we learn is that, you know, if the variable that I want to estimate and the data that I'm using to estimate something else, they are becoming uncorrelated, my estimator is dominated by the a priori. Okay? Let me write here. Let me write here. So, what is an estimator? Okay, the NMC. The NMC has this shape, so it's mu theta plus it is a Cx theta, C theta to the minus 1, no, C theta x. Cx x to the minus 1, and then it is x minus noise. This is what we saw. So now, if this, which is collecting the correlation between the parameter to estimate and the input, if this guy is going to 0, this disappears, right? Okay, now what wins is mu theta. What is mu theta? Mu theta is the a priori information. So what wins is the a priori information. Actually, it's the mean for the a priori information. Now, why that guy is going to 0? Magic answer. Why that guy is going to 0? So if sigma is going to infinite, the output, the filter is 0. Okay? If the filter is 0, means that, you know, I cannot say anything. Means that the estimator is 0. Means that, you know, in that specific case, okay, this was just a recall of the theory, but you know, in that estimated case, the estimate on y hand is 0. Why is 0? Why in your potential application you would find 0?
Because it's mean value.
Because that's the mean of the a priori information. The a priori information says that the random process are Gaussian and are 0 mean. So the main motivation is that everything we are working in, and specifically according to the block diagram, y is 0 mean. Okay? And since y is 0 mean, it is, so I expect that the solution is 0 because it is the a priori. In other words, if you want to see this estimate, you know, I mean, it's a trade-off between this one that's a mean of a priori. And this comes from the data. But now what's happened? This is balancing what comes from the data and what comes from the a priori. If this one is 0, this term disappears, so the a priori wins. Okay? Remember that. Because I know that one day you will be surprised because you get the estimated value which is close to 0. And then you cannot understand why. Okay? Those that will be surprised on that are the telecom, mostly. Because in their life they will find several applications mostly dealing with signals, that using the MMSC estimator, you will find that your signal is, it's good, but you know, it's too small. Okay, that's what you tell me. And then you know the answer is easy, is you know it is too small or it's pulled to zero, because I mean the MMSC, when it doesn't know what to say, it's shut up. Okay? Which is the golden rule. Okay? So you know that's the estimator. Now, this is the intuitive part for going to infinity, which is analytically what we get. Now what's happened for sigma square going to zero? Well, if sigma square goes to zero, you know, I have exactly the filter that I was mentioning before. Because if this guy, if sigma square goes to zero, these disappear, then this one and that one simplifies. You see? That is exactly the solution that I told you. So essentially, you know, the Wiener filter is trading between two extreme situations, where it's better to shut up, which means better to put to zero, or it's better to make exactly the ideal filter that you might imagine. Now, the filter response is infinite. Now, is it clear, Paul? I took a while, but you know that my goal is to show you side information and to consolidate all that we said. Now let's touch the part of the problem of the exercise that you are mostly supposed to know. Okay? So my goal is now, so I'm solving now the B. So I want to estimate the MMSC by the MMSC criteria using 3 samples for any arbitrary sigma W, and compute the linear estimator, okay, which is y equal h prime x, and evaluate the 3 possible values of h for the limiting case of sigma square going to 0 and sigma square going to infinity. Now, okay, now you know, even if a sigma square, now it's different from the previous exercise, because now I'm using 3 values. I'm not using infinite values, I'm using 3. So I keep on passing the figure. So I copy the figure and I solve this one. Page. Yeah. So now, what I want is y hat n is equal to a set of coefficients, so it is h minus 1, h0, h1. Multiplied by x n minus 1, x n plus 1. This is what I call x n, and this is what I call h transpose. Okay. So my goal is to get the MMSC estimator based on the three values, which is n minus 1 and then n plus 1. Now, first of all, you know, I solved the first Wiener because to say that if I want a Wiener estimator, that means that, you know, I mean, I need to calculate a pole or a set of pole. No, so having a pole in a partial response means that the estimator is infinite. The Wiener estimator is optimal because it's very, very long, you know, it's infinite long. So what I expect is that the mean square error for a Wiener estimator is less than this estimator, because I'm using 3 values. Because the Wiener is using infinite, and here I'm using 3. Okay. So what I expect before touching the equation, you know, something that is triggering my brain. So the mean square error, okay, for Wiener is smaller than the mean square error for this H optimum. Okay? That's because the length is infinite versus the length is equal 3 in this case. So what I expect that, okay, because H, so the vector H now is 3. The size of vector H, okay? Now, if the size of H is going to infinite, which means in my hypothetical estimator, I take this set of coefficients and, I'm using more and more and more, which means infinite. What do I get? Of the Wiener filter. Okay? So what I get in this way, I get a Wiener filter. Okay? Just to play a little bit on the concept. Just to stress the point that I'm using a limited support, a limited length estimator. Now let's make it. Okay, so that's a y hat. So in order to estimate that, I need to impose, since the estimator is linear, it's Gaussian, everything is Gaussian, which is very nice. Then what I do, what I mentally prefer to do is I prefer to write the orthogonality condition. X n, then it's x n transpose equals 0. Okay. So for the estimator, I'm using orthogonality condition. Now, I'm doing the similar step as I did for the z-transform, except now that I'm doing with the vector of samples. So H transpose, which is the MMC, if you like, is time expectation of xn transpose is equal to expectation of yn x n transpose. Okay. So what I need to compute, two terms. The first term I need to compute these 3 times 3 matrix, and I need to compute these. Okay, now it's a row, but so it's 1 times row. 1 times 3 row vector. Okay. How to compute that? By simply looking at the problem. There is no other way. So let's get practice on this. Now, about computing the first term, it's the easiest one, because this matrix, is dependent on Rxxk. Okay, that's the easy. This one needs work. The second part needs work. Okay, it needs some work to manipulate a little bit. So let's continue on that. Clear up to now? Okay, so it's, once you get practice on that, they're all the same. Okay. So my job is to make every exercise to be slightly different from the others, but sometimes it's not that easy. But they're all the same. Now, so you see why, I keep on having a block diagram. I transport the block diagram through the exercise. Okay. My goal is to transport to the block diagram. It's not because it's useful, but that's because I want to show you that if I have a block diagram in front of me, I can make some reasoning. Now, why doing the reasoning? Is because from the reasoning you can understand if you made a mistake. Okay, assume that you make a computation, then you take these limits, which are very easy. Sigma, blah blah, going to infinity, going to zero, And this way you can cross-check if you made a mistake by manipulating the corresponding formulas. Now, so what is expectation of x transpose? Okay, I write it in a compact way. So then this is the autocorrelation in 0. Then let me see, we have x n minus 1, x n plus 1. So I order, then it's rxx1, rxx2. Then it's tuple structure. So it is rxx1, r. Rxx0, Rxx1, Rxx2, Rxx1, Rxx0. So that means I need to calculate the autocorrelation of x, which means, Rxz. Okay, we calculate, so it is sigma w plus 1 plus z minus 1, 1 plus z, so it is sigma square w plus 2 plus sigma square w, sigma square plus, so it is z plus z to the minus 1. Okay, that's the alpha. So that means that my matrix is simple. Okay, 2 plus sigma w, 1, 0, 1, 2 plus sigma w, 1, 0, 1. 2 plus sigma w. Okay, that's the matrix Rx. It's a triplet structure. Notice that it's not always the same. It's not always guaranteed, but in this case it is guaranteed. I can make another example, for instance, where I show you that the structure is not triplet. Okay. I would make it, quite easy. Now, by the way, this matrix is also banded because I have, the first upper and lower diagonal and nothing else. So anyway, now let's compute the most difficult one. So what I need to calculate is, let me reorganize a little bit the text. So I have more space. Okay. Now I need to calculate expectation of yn, and there is a vector of x n minus 1, x n plus 1. That's all I need to calculate. So I need to calculate the expectation of yn xn plus minus I plus minus k. So the most general is expectation of yn xn minus k, where k equal 0, plus minus 1. Okay, that's all I need. Now what is x? So x, you know, is comes from alpha. What is y? Y comes from alpha as well. Okay, so let's write the way they come. They are corresponding to alpha. By the way, in x there is also w. So when I correlate w with y, since w is uncorrelated with respect to y, so in my computation this is equal to 0. So that means, just for the sake of when you go back and you revisit to everything, okay? So if I call this signal in the middle as, so x, y, alpha, and you call beta, beta n, okay? So that means that this expectation reduces to the expectation of yn beta n minus k, okay, due for the uncorrelated noise property. Okay. Now, to compute that, you know, I need to apply the property of y and the property of beta. So let's do it. Once again, I copy my small block diagram. And I recall that I call this guy as the beta n. So I need to calculate the expectation of yn beta n minus k. Now, what is beta? So beta n is equal to alpha n plus alpha n minus 1. So I go back to the finite difference equations. And the yn is equal to alpha n minus alpha n minus 1. So now I put these two terms inside here. So when I put these two terms inside here, I have expectation of alpha n minus alpha n minus 1, expectation for, it's a beta, so beta is that one, so it is alpha n minus k plus alpha n minus 1 minus k. We remember that k is equal to plus minus 1. Okay? So, you know, everything depends on the autocorrelation of alpha, but you know, the autocorrelation of alpha is is a delta, okay? So recall that autocorrelation of alpha k is equal to delta of k, okay? That's for the autocorrelation. So now applying that, so I have the first term here, which is autocorrelation of alpha, so it is alpha n minus k. Now this is different from 0 only if k is equal to 0. Okay. So then, you know what I need to make a set of distinction. Now, if k is equal to 0, okay, then I have the expectation of, now I make it by hand, so I have alpha n, which is alpha n squared. Okay, so this is equal to 1. Then I have alpha n minus 1, alpha n is uncorrelated, 0. Okay, then I have alpha n minus 1, 0. Then I have alpha n minus 1, alpha n minus 1, okay, which is 1. So if k is equal to 0, then this is equal, oh, by the way, this is 1 and this is minus 1. Okay? So for k equals 0, the correlation here is 0. So the results, I don't know what you call, are, what was that, y beta k equals 0, equal 0. So k equal 1. Now, if k equal 1, let's make it the same. So I have alpha n minus 1, 0. Then I have alpha n minus 1, alpha n minus 1, 1 minus. Minus 1. Then let's continue. Then I have alpha n minus 1, which is minus 2, 0. Then I have alpha n minus 1, alpha n minus 2, 0. The result is minus 1. Okay. Now, I have the other, which is k equal minus 1, ry beta, k equal minus 1 is equal to. Then I have alpha n minus 1, which is alpha plus 1, 0. Then I have alpha n minus 1, alpha plus n plus 1, 0 again. Then here I have alpha n minus 1 minus 1, which is 1. Then I have alpha n minus 1, alpha n, which is 0. So we build our cross correlation vector. Okay? So our vector, so our system is that one time this. So let's see. It is 2 plus sigma square 1, 1, 0. 2 plus sigma square 1, 2 plus sigma square 1, 0. Our h equal to the vector, which is minus, so minus k beta minus 1, which is positive k, so it is minus 1, 0, plus 1. That's my estimator. So, inverting the matrix for different alpha, I get the estimator. That's the MVC. Now, I don't remember if the problem was asking in any case. What about what's happening if, is it clear? What's happening if a sigma square is going to infinite? Now, it happens that this matrix becomes a diagonal dominant. Is diagonal. Okay? So let me change the color so that it highlights different. For sigma square going to infinite, then my problem becomes is H, which is so it's a diagonal matrix which is dominated by infinite, so it's the inverse of an infinite, okay, which is going to 0. Then H is going to 0. Similarly as before, and as as I expected. For sigma square going to 0, okay, which means that I have no noise. Now, this is beautiful, because what I'm doing is, I need to have a pole. You remember the system? The system is the following. If I have no noise, okay, I have no noise at all, then my goal is to estimate this guy using that. But if I want to estimate this using that, what I need to do is I need to invert this filter. But to invert this filter, which is composed by 0, I need pole, right? But now, in my system, I'm not using pole. Because, I don't have the possibility to generate a pole. So, my solution, the solution that I get, is a solution which is approximating the pole, which is the pole due to this this filter here. Okay. And so since this filter looking at this, it's a 1 plus z to the minus 1. So what does this is 1 plus the previous one. So 1 plus the previous one means it's similar to integrate, it's making the average approximately. Okay. So making an inverse for that is doing a kind of derivative. So that's the reason for having these two different sign values. It's because, the inverse of a filter, which in principle ideally should be a pole with an impulse response which is infinite, is approximated by a filter that has, has only 3 values. And these 3 values are numerically computed by this way. So if you have a MATLAB, we can also get the 3 values. Okay. Then that's it. The exam is finished, okay? So once you get practice, we took a huge amount of time to make this because this was the first one. Huh? But once you get practice, you do it quite quickly. Let's start with the second one. This is taken from the 25th of July 2017. No, we start solving it, and then we get the coffee, and then we come back. Now, consider a set of signals y1 and y2, which is obtained by x1 and x2 by this set of combinations. Oh, I wasn't mentioning that I wanted to modify the exercise before to make the matrix which is not a duplex. Okay. Now, let me make here. So my goal is to show you that the matrix is not always duplex structure. And then I take the opportunity to mention that if it is duplex structure, the process is stationary. Now, so let's assume we have that exercise here. So let's assume that I tell you now that I want to use x and y to estimate alpha. Okay? So, imagine I modify the exercise as following. I have alpha n, and then I have 2 filters. As it is indicated by copy just. It's 1 plus z minus 1, 1 minus z minus 1. Here I have noise W1, and here I have another noise W. This is xn, this is yn. Differently from the previous exercise, W1 and W, there exist 2 noises, the 2 noise effects. Because otherwise, if I don't put this noise effect, the way to estimate the alpha is trivially done, because I simply invert this. Okay? So how do I get alpha? So imagine that I estimate alpha by simply combining, x and y. So my new estimator is h1, h2 multiplying by xn and yn. I'm modifying that and changing. Okay, so this is h, and this is x, y. We call f. Okay. So now that's as similar as before. Okay, so I use the orthogonality. So by the orthogonality, let me write. So I go a little bit faster now. So from the orthogonality, I get that my optimum filter is obtained by taking f transpose multiplied by h minimum mean square error equal to the expectation of, and then I have alpha n time Fn. Okay. Now, looking at this one, here I have the expectation of xn with itself. Okay, so I here have the expectation of xn squared. Here I have yn squared. Here I have xn yn. I choose two simple examples to show that it's not perfect. I could have chosen another example, that's okay. Okay, so now, so what is the power of xn? Now, the power of xn is equal to 2 plus the power of w1. So that one is 2 plus sigma squared w1. And the power of y is 2 plus the power of w2. And what is the cross correlation between here is expectation of xn and yn. Okay. Now, so it's the expectation between these two guys. But so if I calculate x and y, then it's w1 and w2 are statistical independent. So I calculate the expectation between this and that. So we call this one is beta 1, beta 2. Then this part is equal to the expectation of beta 1n and beta 2n. Then to calculate this expectation, I need to recall the finite difference equations. So I need to remember that the beta 1 is obtained by alpha n plus alpha n minus 1, and beta 2 is obtained by alpha n minus alpha n minus 1. So I simply substitute here. So I get expectation of this alpha n plus alpha n minus 1 times alpha n minus alpha n minus 1. Okay. So it's a monic, so it is, so I have alpha n squared, then I have minus alpha n squared, then I have alpha n minus 1, so this one is 0. Okay. It's a 0 because I have alpha n squared and then minus alpha n minus 1 squared. Okay, so it's 1 minus 1. So this does not exist. Very nice. So 0 and 0. Now the matrix is not perfect because sigma square 1 and sigma square 2 are different. Okay. And then you continue with that. This is just an extension, but while I was telling you that it's triplets, I wanted to show you that.
In the case there is not the noise of W2. It is not triplets as well, right? Or not?
If it is,
If there is not the noise in W2,
then it's not triplets anymore. Okay, yes. But I wanted to generalize.
Okay.
It's only because I wanted to make it more and more general. By the way, when the autocorrelation matrix is Toeplitz structure, that means that whatever you compute the correlation for whatever pair of the samples, okay, the matrix, correlation is not dependent on which pair of samples you use, but it depends on the distance between the pairs. Now that's another way to use the definition of stationarity, because if you have a random process, the random process is stationary, then the autocorrelation is tuplets. That's a general property. Let me write to you here, so perhaps you meditate a little bit. So, if xn is stationary, then anytime you calculate the expectation of xn is a vector, as a vector of entry, xn transpose, this correlation matrix is tuplets structure. Okay? And it's also true the opposite, which means if I have a tuplets matrix, if I have a correlation matrix which is tuplets, then the process is stationary. Second remark, if Rx has the property that along the diagonals is periodic, okay, then the process is cyclostationary. Okay. If it is periodic along the diagonals, then xn is cyclostationary. Okay. Now this is just a flavor for a telecom, because the telecom, they work a lot on cyclostationary random process. Okay. Because this is corresponding to the bit communication, where they transmit bits, and bits, are transmitted periodically, and then, process is cyclostationary. Okay, this is just a remark, let me say, comment before going on. Now, let's take another exercise. Let me see if it is this one is better or this. Let's make this first. So let's do this one. It's a little bit more involved. This is the 1st of July. So let's read together. Then here you don't have a block diagram. That means that you need to create it yourself. So I have alpha and beta. Alpha and beta are two statistically independent Gaussian random process. Okay, white random process, and you generate two signals by two filters. So I have alpha, and here I have beta. Okay. Now, so beta, is obtained by taking alpha, filtering by taking y, filtering y, and then summing beta. So let me make a block diagram here, because rather than having a block diagram which keeps going, I sketch here, it remains, and then I can avoid to just copy and paste the block diagram. So let's read. Now I have y, so I have alpha, and which is entering. It's entering into a filter. Now the filter is 1 minus 1/2 plus 1/4. Then I generate y. Then I get x. Now x is obtained by filtering y by 1, 0. One minus d to the minus 1, summing beta. And this is called x. Okay, so this is the block diagram corresponding to this part. Now, let's read. Wait a minute. Okay, so let's read. I don't see anymore. Okay, characterize the process yn and evaluate the autocorrelation sequence R, Y, Y. Here, yn is an autoregressive process. It's autoregressive 2 poles. Okay, so it's, this guy is autoregressive order 2. Let me write it. So compute the autocorrelation. Now, to compute the autocorrelation on Y, I need to use a Euler-Walker. So, which means, let's write it. There's no other way. Let's write a Euler-Walker and compute. Let's see if I can do it now. Okay, I'm using a new page. So the Euler-Walker is this one. So let me write, to simplify, let me write R1. So I indicate in this way Ri as Ry, Yi, okay? Just to make it compact. So from Euler-Walker, the right Euler-Walker, not the one that you put into the intermediate formula, okay? Have you seen? I have to correct the formula that you gave me. Who made the Euler-Walker? Who wrote the Euler-Walker this way? Anyway, nobody used. I'm lucky because nobody used. So you wrote a Euler-Walker, but then nobody used the Euler-Walker because everybody, those that used the Euler-Walker, they did it the right way, and so nobody copied that formula, which was the vector of the exam. Now, so the Euler-Walker is Ri. Then it is, what is the filter? Minus 1/2 Ri minus 1 plus 1/4 Ri minus 2 is equal to sigma square of the input times delta I. And the input is 1. Okay, so this is 1. Okay, this is the Euler-Walker. Now let's apply that. So I start writing R0 minus 1/2 R1 plus 1/4 R2 equal 1. Then this is for I equal 0. Then I write for I equal 1, which is R1 minus 1/2 R0 plus 1/4 R1 equal 0. And then I write for I minus 1, which is R minus 1, which is R1, minus 1/2 No, I need to use 2. Otherwise the matrix gets a singular. R2 minus 1 R1 plus 1/4 R0 equals 0. Okay. So it's a system of equations. Then I collect R0, so these are my unknown, and then I have a known term which is 1, 0, 0. So this is 1 minus 1 half, 1/4. Then I have 1 minus 1 half, 0, and then it is 1/4, 5/4. Then it is 1/4 minus 1 half, then it is 1. Okay, so I need to solve this system of equation. I'm solving, then I get R0, 1, and 2. Okay. Now, this is the time where you get the laptop. Compute that. Okay. So I open the MATLAB. I don't remember if I already solved it in the text. I don't know, I made it now. I launched MATLAB. By the way, there is MATLAB 2018, which contains several new functions, mostly for statistical results. Okay, open. Now, R equal. Can you tell me what is written so I make it quick? What these are? The matrix are. Can you dictate me?
Like column or row?
No, row.
1
1,
minus half,
0.5,
a quarter, 1/4,
0.25, second line,
minus 0.5,
second row,
minus 0.5.
1, minus.
Yep.
Minus point minus 0.25,
0.5, 5/4,
4,
0,
0,
then
third,
1/4, minus 0.5,
minus,
yep,
minus what?
0.5,
0.5,
and 1.
okay, 1.5, 0.25, 0.25, 1.25, 0. I don't know. The second is minus 1 half.
Yeah, 0.5.
Minus 24. 1 half, 1.25, 0, 1 half, minus 1/4 to 1 half. And 1, perfect, okay. And then the vector is 1, so you know I get in of this R multiplied by a vector of 1, 0, 0. Okay, so R0 solving here. 0.2 minus 1 point. No, point 17. Okay. Now, let me see what is the request. Okay, so describe process, evaluate its correlation sequence. Perfect. Characterize the process accent. Now the process accent is ARMA plus a white noise. Okay? That's I know because I have a Poland chip. And evaluate its autocorrelation sequence are accent. Okay? Now to compute the autocorrelation of X, I need to calculate from the autocorrelation of the Y here. Okay? So computing that one. So to compute R X K is by Z transform, and which is equal to 1 minus Z to the minus 1, 1 plus Z to the minus 1 time Rx R Y Y Z. So this one is 2 1. Oh, there is a mistake. 1 minus. Did you realize? No. Okay. Now it's right. Okay. So it's 2, and then it's minus Z plus Z to the minus 1 multiplied by R Y Y Z. Okay. So this means that R X X K, for instance, is obtained by 2 times R Y Y K minus it is R Y Y K minus 1 minus again R Y Y K plus 1. Okay, that's how to compute. So how to compute autocorrelation for R. This was part of the intermediate exam. So, you know, this is equal, so it is equal to, now I need to see what was the value. So it was 2 times 1.15 minus it is 2 times that's for 0. Okay. Rx(x0) is equal to 2 times 1.50 minus 2 times 0.23. The numerical values. Okay. Rx(x1) is equal to 2 times ry1, ry1. So it is 2 times ry1, it is 0.23 minus, it is 1 minus 1 is 0, so it is 1.15. So this one is RYY1, this is RYY0, and then I have minus R1 Y2, which is minus 0.17. And then I compute it. Okay.
Is missing maybe beta or not? Because X has also beta design. Yeah,
I forgot.
Plus sigma square beta, right? Plus sigma square beta times delta k. I forgot. The beta is parametric or unitary? I don't know. Power 1. Okay. It's 1. So it is plus 1. And all the others is okay. Thanks. And so on. Okay? Now, remember, cross-check that you can always do is that, remember, okay, warning. Rx(x0) should be larger or equal than Rxx(k) for any k. Okay, remember that as a cross-check. This is an absolute value, so more than absolute value of Rxx(k), okay, for any k, as a cross-check. So I don't put Rxx0 because I mean it's a power, and power is positive. Now, we continue on that, after coffee.